Welcome. In the last class we saw a method to estimate the partial molar volume from the data obtained from mixing experiments. In other words, the experiment is essentially mix a certain number of moles of one component and a certain number of moles of the second component together. We know their initial molar volumes, and if we measure the final molar volume, we can figure out the difference between the molar volume of the solution and the molar volumes of these individual components. And with the change in molar volume plotted on the y axis as a function of the mole fraction of the second component, we said that we could estimate the partial molar properties. For example, if this AGB is the curve that gives the variation of the volume change upon mixing as a function of the mole fraction x2, then if we are interested in finding the partial molar volumes, say at a mole fraction of E, then all we need to do is, to the curve AGB at the point E, we draw a tangent, and where the tangent meets the y axis, this intercept would give us V1t bar. The basis for that was brought down to this equation, which could be geometrically interpreted, or these have meanings as lengths on this graph. For example, delta VE, the volume change on mixing at the mole fraction given by the point E, is nothing but this length GE, because that is the point that corresponds to the curve at the mole fraction which is given by the point E. So GE is that distance, or EG is that distance, times x2E could be AE or CF, they are the same lengths. So AE times GF by CF, which is essentially the slope of the tangent to the curve at the point G as given by dou x2 del V at the point E. So this is the slope, and we all know that AE equals CF, therefore these two can be cancelled, therefore it becomes EG, which is this length, minus GF, which is this length, which is actually FE, which is the same length as CA, which is the intercept on the y axis of the tangent to the point G. Therefore that was the way to find out the partial molar volume V1t hash. I have been using hash, dash and bar, please take them as being used interchangeably, they all mean the same, at least in this local context here. So V1t hash, and this was given as an exercise to you. I had asked you to work out a similar geometric interpretation to find out the partial molar volume V2t hash, and the formulation would yield that the difference here V2t hash minus V2 at a point E would be equivalent to the intercept on the other axis, and therefore we could find V2t hash from there. So that hopefully you went about completing that exercise. Today let us start out by working a problem to estimate the partial molar quantities. It is a problem of current significance, example 4.1. The biofuels have the potential to meet a significant fraction of our energy needs in the near future. Lipids from algae or plants are an important source of biofuels, especially biodiesel, or it could yield many different biofuels. In one of the steps to extract lipids from cells, the methanol water system is used to extract lipids. During studies on optimization of the extraction procedure, in fact this is something that we did in our lab, so I kind of picked it up here. During the studies on optimization of the extraction procedure, a PhD student needed 30% mole percent methanol in water system. The student who actually did that, or the person who actually did that in our lab, was a project associate. in this case anyway, PhD student needed 30% given as mole percent methanol in water system to prepare 2 liters of the needed solution. What are the needed volumes of pure methanol and pure water? The lab is maintained at a comfortable 27 degrees C. This is a very standard thing that comes about in day to day requirements while working with these kind of things. And let me also give you some data before going forward. The data is that the pure species molar volumes at 27 degrees C for methanol and water are given, that is 40.73 centimeter cube per mole for methanol and 18.07 centimeter cube per mole. I think we said we will remember this value, 18.07 cc per mole for water. The partial molar volumes are also given 27 degree at 27 degrees C. For methanol it is 38.64 centimeter cube per mole, and the partial molar volume is 17.77 centimeter cube per mole. Note this difference right here, 18.07 for the pure component, whereas in this particular case it happens to be 17.77, a significant difference here. Okay, what I would like you to do is think about how would you go about solving this. Yeah, why don't you think about it, and then I will give you a couple of hints and some more time to work it out. Since this would require essentially definitions and use of some fundamental concepts which you have been learning from the school stage, take about 15 minutes and try to come up with the solution on your own. It is very doable, and anyway I will give you the hints after 15 minutes. Go ahead. Okay, let me give you the hints that I mentioned earlier now. Some of you would have worked this out for sure. I hope that many of you were able to do this, but in any case some hints in case you have not been able to do it. Use the basic definition, summation of xi, the mole fraction, times the d of the partial molar quantity, d mit hash equals 0. That is the first hint. The second hint is something related to a concept which is very simple, but which I have found many students to have difficulty with even at an advanced stage. That is the definition of a mole. It is a very simple concept, please pay attention to that. I will tell you more about it when we come back. Since it involves something that I find many students have some difficulty with, I will let you figure it out on your own and give you some time to do it. Take another 15 minutes to come up with the solution. If you already have the solution, you can just fast forward to the point where the solution begins. Go ahead please, otherwise spend about 15 minutes more. You have a lot of time to feel comfortable and work out the solution. 15 minutes. Okay, now let us look at the solution from the hints that were given. Let us use sum over xi dmit hash equals 0 and the definition of a mole. The mole, as we all know, is defined as the mass by the molecular mass of a substance, that is 1 mole of a substance, or if you divide the mass of the substance you have by the molecular mass, you get the number of moles. It is as simple as that. Now let us look at the solution itself. We know from equation 418, which is just given to you, that sum over xi dmit hash equals 0. This was given as the hint, and therefore for our binary system, in this case methanol and water system, the solution molar volume can be written by expanding this. The molar volume of the solution is nothing but x1 V1 hash plus x2 V2 hash I have just dropped the T's there for convenience, nothing else. We can take one to be either methanol and 2 to be water or the other way. Let us see what I have taken here. We substitute the values. I have taken 1 as methanol and 2 as water. The molar volume of the solution is 30% methanol, therefore 0.3 is the mole fraction of methanol. 0.3 into the partial molar volume of methanol 38.64 plus 0.7, that is the mole fraction of water, times the partial molar volume of water, that is 17.77. If you do the calculations, it will turn out to be 24.3 centimeter cubed per mole. So, this is something that we need to calculate for whatever we need to do. We need to essentially find out how much of these two solutions we need to mix to get 2 liters of the total solution. The total volume needed is 2 liters, which is 2000 centimeter cubed. We have these in terms of centimeter cubed, and therefore, let us also convert this into centimeter cubed, that is 2000 centimeter cubed, and the total number of moles that is required, this is N, this is the total volume divided by the molar volume. In other words, if 1 mole occupies 24.03 centimeter cube per mole, how many moles would be required to occupy 2000 centimeter cube? That is the unitary method that we are using here. Therefore, the number of moles is 2000 divided by 24.03, 83.23 moles is what it turns out to be. So, this is the total number of moles of the solution that we need. Therefore, the number of moles of methanol for this solution is, it is a 30% solution, right. So, number of moles of ethanol is nothing but 30% of 83.23, or in other words 0.3 times 83.23, it turns out to be 24.97 moles. And the number of moles of water is automatically 83.23 minus 24.97, or it is 70% or 0.7 times 83.23, that is 58.26 moles. And therefore, the needed volumes of pure methanol and pure water, this is what we needed to find to make up the 2 liters of the required solution, 30% methanol solution, is nothing but 24.97 times 40.73. We got this 40.73 in this is the number of moles, and this is the molar volume that was given to us right in the beginning. Yeah, let us go back and just check it out here. Yep, the molar volume of methanol was 40.73 centimeter cube per mole, and the molar volume of water was 18.07 centimeter cube per mole. So, the number of moles into the molar volume will give the volume of the pure component, and that is what we are doing here. Okay. So, number of moles, which is what we found out, times 40.73 molar volume turns out to be 1017.03 centimeter cubed, and volume of water is 58.26 number of moles of water times the molar volume of water 18.07, 1052.76 centimeter cubed. So, that brings us to whatever we need from the problem. Okay. The next thing that we are going to look at is something called excess properties, and what we will also do is see a little later, after we look at excess properties, how to correlate the activity coefficient to the excess properties, or in other words, we will come up with a method to estimate the activity coefficient from the so called excess properties. But first let us look at what excess properties are. to understand excess properties, let us review residual properties, okay, to give out the secret what residual properties were for pure substances, excess properties are for solutions. It is as simple as that. Okay. Here we saw that in module 3 that the difference between the actual value and the ideal value of the thermodynamic property, any extensive thermodynamic property, is called the residual of that property. Remember that Mr equals M minus M ideal gas. So, in other words, for any extensive thermodynamic property M, it could be internal energy, entropy, enthalpy, Helmholtz free energy, Gibbs free energy, or volume for that matter. The residual property was, as mentioned, this. This was equation 325 that we saw earlier, and we had used the residual properties extensively to estimate the various thermodynamic properties, and that's the utility of these residual properties. It is a very simple definition, but it comes in handy because the data is easily available in terms of residual properties. A similar formulation for solutions, that was for the pure substance, this is for the solutions or mixtures, is called excess property. An excess property of a solution, as you would have guessed, is the amount by which the relevant thermodynamic property exceeds that of a hypothetical ideal solution of the same composition. Okay. You need to keep this in mind. We are taking the difference between actual and ideal. The ideal is hypothetical, it does not really exist, it is what it would be if it is ideal. Thus, if the excess extensive total property is represented as MTE, I am going to use the superscript E to denote excess properties, the same way that we had used the superscript R to denote the residual properties for pure substances. So, MTE and the hypothetical ideal solution property as MT comma ID, ID for ideal, then the excess property MTE is defined as the difference between M, the actual property, and the ideal property, MT ideal. Let us call this equation 423, and what we are going to look at in detail is one such excess property, namely the excess Gibbs free energy. Therefore, when we start up the next class, we will look at excess properties, which is nothing but the difference, to repeat, the difference between the actual property and the hypothetical ideal property, and we are going to look at the excess Gibbs free energy.